dreaming it up in the first place. But once you're given it, it's pretty easy to find. I mean, you know the expression for L hat plus. It is Lx plus I Ly. Okay, and you've got polar angled expressions for Lx and Ly. Like here's the Ly one. So you can apply these to these. So show that this equals that. All right. Now, why am I saying that? Well, remember the right-hand side of the new expression we had j squared into alpha something plus beta something. Right. Well, now instead of j squared, write this. So then apply all this to the alpha something plus beta something. Okay. Hope you're following. All right. Okay. So now applying all this to your alpha something plus beta something, you will get. So we now have two relations involving alpha and beta. So one is the original equation, the one I ID'd with star circle. That has an alpha, a beta in it. We have another, with this j squared, and we have another involving alpha and beta, and that's the normalization condition, right? Alpha squared plus beta squared is 1. So you have two equations, and you got this one as well here with the j's in it. All right. So solve those equations, and eventually you'll get something like this. Now these terms we've just seen before. That's from the star circle equation, the alpha beta equation. But now we have terms here. Now we have terms for, that's your alpha and that's your beta. Right? You've now solved for alpha and beta. And your J ends up being L plus or minus a half. Right? So you've solved for your J. So actually it's like 3 equations. Huh? It's the normalization condition and 2 others, because you've got 3 unknowns. So you've solved your alpha, you solved for your beta, and you've got solved for your J. Right? Now, yeah, like I said, it's getting harder. So if you appreciate a good challenge, then go to it. Or, for those of you who are planning to go on to master's level quantum mechanics, on the addition of angular momenta, you can wait until then. So, right? Now, why do this? What's the motivation for doing this kind of thing? Well, the next example we'll give will be, there is a coupling. Now, remember before I was assuming an independence between the orbital angular momentum and the spin angular momentum, but that's not always the case. There was a simplification in the model, but when you're dealing with increasingly finer, how can I put it? When your modelling becomes closer to the real world and you include more and more factors. So in fact there is a small coupling, a magnetic coupling between the angular momentum and the spin angular momentum. So when you bring that into your model, it turns out, it's not obvious right now, but it turns out that expressing your J eigenstate, like J, M, in these terms is actually very useful, very helpful. So that's the motivation. So this is a kind of stepping stone for future work, and the future work is dealing with the quantum mechanics of the interaction between when the angular momentum and the spin angular momentum influence each other. They have an effect on each other. One generates a force on the other one, and so forth. Okay. Now I mentioned this bit before, but the alpha beta from the previous section, they are examples of Clebsch-Gordon coefficients, and these things feature heavily in angular momentum theory and quantum mechanics at graduate level. Like if you really like group theory and representation theory of groups, then Clebsch-Gordon coefficients will be very familiar to you. Okay, now I'm finishing off. I'd like to do a little bit of boasting. About once a week, 2 weeks, probably more, maybe 2 weeks or so, a couple of times a month, I Google this whole series of lectures, deGarisMPC. So I put that into the search window and just see what, I got about 3,500 hits now just on that term alone. So I searched through. I'm just curious to see what people are saying and what's going on. Now, one of my longer term goals is to eventually wipe out the teaching side of universities, so that millions of parents, hundreds of millions of parents, can be saved of having to spend huge amounts of money on the education of their kids. Last night, for the first time, as far as I know, I saw concrete evidence, very concrete, of an academic institution now referring my lectures, these deGarisMPC lectures, to their students. If you're curious, you can look up this institution. It's the email is, let's say it's URL, so its website link is itt-tech.edu. So it's an institution, and they claim they have 140 campuses across the US, and they're heavily into online teaching now, and they're referring students, bachelor level students, and of course this coursework is still at undergrad level, but they're referring their physics math students to these courses, and that's the first time that I've heard that happen, which is a nice stepping stone. So I hope if other institutions like the stuff, they'll do the same. But my real aim is to try to inspire other, especially retired professors, to do the same, to do a kind of mind dump, put their knowledge on YouTube, on the internet, so that when they die their knowledge is not lost, so that the world can benefit from their knowledge, which I see as a noble goal, and with the very positive side effect that it makes education a lot cheaper. Now, also last night I was thinking some types of professions, professional training, you can't really do only on the internet. Like, imagine you're training to be a dentist. You can't do that online totally, right? I mean, suddenly you got to start working with patients. Or if you're trained to be a doctor or a surgeon or something, you still need on the site, SATE. You need on the site training. So it's more for specialties like mathematics or physics or that kind of thing. Sort of pad and pencil type specialties where you could pretty well totally wipe out the teaching side in a classroom. So I'm going to have to nuance my goals somewhat you know, the on-site practical type education, you'll still need classroom, well, lab type teaching. So I need to qualify what my goals are to some extent. So, ciao.